The first kinematic equation we learned in one-dimensional kinematics is the same one we're going to start off with in two-dimensional kinematics. Remember the stuttering vat? We use that equation to find out an object's final velocity. We're still in the ideal world here, so we won't take into account things like air resistance.
However, since we're in a plane, we do have to worry about the x and y components of the object's velocity and acceleration.
Okay, the first two-dimensional kinematic equations we're going to look at are used for projectile motion problems. But before we can get down and dirty with these equations, though, we've got to know how to find the magnitude of a projected object, so we can use it in our equations.
Now that we're going to get into some heavy equations, we'll represent vectors in heavy, bold type. Let's say a cannonball is shot out of a cannon. The initial velocity of the cannonball makes an angle theta with the ground. Remember that velocity is a vector, so it has x and y components. And remember how we found the magnitudes of the components? Well, the magnitude of the x component of a projected object is found using the formula v sub ix equals v initial times the cosine of theta. And the magnitude of the y component is found using the formula v sub iy equals the initial velocity times the sine of theta. So these are the equations for finding the magnitudes of the x and y components of a projected object's velocity.
We also have to learn a special number. Just learn it, love it, and keep it in your back pocket for later. It's the acceleration due to gravity. You know, when the apple fell on Isaac Newton's head, he figured out that there must be a force that makes the apple fall down. But since this is a dramatization of actual events, we have used our artistic license to embellish a little.
The acceleration of any object due to gravity at the surface of the Earth is 9.8 meters per second squared.
Since gravity creates a force pulling an object down towards the Earth, then it is the y component of acceleration, because we've drawn the y-axis up and down. And on the y-axis, assuming up is positive and down is negative, a sub y equals negative 9.8 meters per second squared. But since we use it so much, we'll just use a little g to represent the acceleration due to gravity.
Now that we're a little more knowledgeable about gravity, it's time to get our hands dirty with the projectile motion equations.
The first projectile motion equation is easily derived from the first one-dimensional kinematic equation we learned, our old friend VVAT.
That equation is final velocity equals the initial velocity plus acceleration times time. V sub f equals v sub I plus at. For projectile motion purposes, we modify this equation to find the y component of the object's velocity. Why the y component? Well, that's the up and down component that corresponds to the acceleration due to gravity. The y component of velocity starts out positive as the object moves away from the Earth, gradually drops to 0 when it stops getting higher, and is 0 at its highest point. Then the y component of velocity gets negative as the object falls back towards the Earth. That is, the object finally falls faster and faster. So then the object's y component equals the initial positive velocity plus negative gravity, because the acceleration due to gravity goes downward times time.
So, since we're only dealing with velocity in the y direction, to get our first projectile motion equation from our VVAT equation, substitute v sub y for v sub f, v sub iy for v sub I, and negative g for a. Then we get our first projectile motion equation. V sub y equals v sub iy minus gt. Got it?
Now, the horizontal velocity stays the same during the flight because there's no acceleration in the x direction, only in the y direction. That's why in the first equation, we don't worry about the x component of velocity, because v sub x equals the initial velocity in the x direction, v sub ix, all the time. And that's our second projectile motion equation. V sub x equals v sub ix. The x component of acceleration is 0 for any object undergoing constant velocity, because the object does not speed up or slow down in the x direction. Remember, we're in the ideal world here. But in the y direction, the object goes up, slows down, stops, and then falls faster and faster. So remember, our second projectile motion equation is v sub x equals v sub ix. Got it?
The third projectile motion equation helps us find the distance that an object has traveled in the x direction. This equation deals with the position of the projected object, and it looks like this.
X final equals x initial plus the x component of the initial velocity times time, or x sub f equals x sub I plus v sub ix times t.
The fourth projectile motion equation tells us the displacement of an object in the y direction.
Y final equals y initial plus the y component of the initial velocity multiplied by time minus 1/2 gravity times time squared. Or y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared.
If you're having trouble remembering where the minus signs are in these equations, they're only in front of little g, the acceleration due to gravity.
Now that we've learned the equations for projectile motion, v sub y equals v sub iy minus gt, v sub x equals v sub ix, x sub f equals x sub I plus v sub ix times t, and y sub f equals y sub I plus v sub iy.
Where v sub ix equals v sub I times the cosine of theta, and v sub iy equals v sub I times the sine of theta. Second, set up those kinematic equations. Gravity is the force pulling down on an object in the y direction. The acceleration due to gravity equals negative 9.8 meters per second squared when up is considered to be the positive y direction. The y component of a projected object's velocity, v sub y, equals v sub iy minus gt. The x component of a projected object's velocity is constant, so v sub x equals v sub ix all the time.
For the distance that a projected object has gone in the x direction, x sub f equals x sub I plus v sub ix times t. We find the displacement of a projected object in the y direction by using y sub f equals y sub I plus v sub iy times t minus 1/2 gt squared. Finally, after we set up the equations, remember to keep your positive and negative axes the same from beginning to end. Then plug and chug and crank. And that's it.
Section B, Uniform Circular Motion.
We've learned about projectile motion. Now let's learn about uniform circular motion. That's when an object moves around a circle with a radius r at a constant velocity v, like when I swing this whistle in a circle.
To watch more free educational videos, visit our website, studioforlearning.tv. Stretch your brain online.